Good morning, good afternoon, and good evening. Guys, today I want to talk to you about underwater inspections of cathodic protection systems, underwater inspections, or inspections of submerged structures. I'm talking about underwater inspections of cathodic protection systems in marine terminals, in underwater pipelines, in single-point moorings, in marine terminals. And I want to thoroughly explain to you precisely how the comprehensive monitoring process is meticulously done, how the essential measurements are accurately taken, and what exactly is how Pedro Morales successfully managed the crucial cathodic protection system of his extensive marine terminal facility. Normally, I had three types of inspections for the marine terminal because I worked for 22 continuous years of service at this company, at this gas processing and fractionation plant, Jose Antonio Anzoátegui, Barcelona, Venezuela. And well, literally, I was the one who managed the integrity plan for the facility. Everything that was underwater was my responsibility. It was the corrosion control and cathodic protection department. As always, the introduction, which is never missing. Then there was another important type of inspection, which involved precisely sizing the anodes and thoroughly cleaning the piles to accurately evaluate the welds on the plates. Because these anodes were securely attached to the piles, they were large 42-inch diameter pipes, specifically API-X42 grade, if I remember correctly. And the fastening system was achieved through the use of clamps, but those clamps absolutely had to be securely welded because normally, with the constant motion of the waves and the powerful force of the wind, there are always significant longitudinal and tangential stresses that originate from the movements of the ships. The massive ships generated significant stresses through these robust mooring systems and consequently caused the flexible metal pipes to noticeably flex and bend under the immense pressure. That's why they're made of metal, because they have to withstand those stresses, and the welds on the anodes would always crack on me. So every year I would have a potential measurement inspection done, and then I would have the anode sizing inspection done because normally I would replace the anodes every 5 to 7 years. But every 3 years I would have that anode sizing inspection done, so I already had a general overview. Okay, so I have this much. I have 146 piles, I have this many anodes, so I need to buy this quantity of anodes and involve underwater welding. Also, we had to meticulously monitor that as well. The thorough cleaning of the anodes was performed entirely manually, as you can clearly see in this detailed video, where we basically had to carefully remove the significant coral formation or the extensive marine life that had developed on the submerged piles. Having the entire pile cleaned is not recommended. Remember that the polarization on the piles is due to concentration, and if there is coral formation, it prevents the marine currents from depolarizing the pipe. So I don't have them clean everything. I was very selective about that because literally, if you remove all the coral formation, that polarization that formed on the substrate, on the layer of the pipe, if the marine current passes through, it will depolarize. So it wasn't convenient. There, with an anode as well, we had to check what the wear was like. Notice the fixing clamp, but all of that was welded. I had to we had to use pneumatic brushes to clean all the welds, and on a few occasions we did magnetic particle testing. But they always had me re-weld all of that kind of as a safety measure. It's better to be overcautious than to have something fail. That's what I always said. Well, I always love doing my inspections, also evaluating the guys. Also, we meticulously performed anode replacements and subsequently had to undertake complex underwater welding operations. It's quite a challenging task. Here, this anode isn't new, it's just that the welds broke and I had to do underwater welding to fix it. Because when we find that the anode doesn't have, I'll explain that to you in a moment. The welding we do here underwater is exactly the same procedure, the same protocol as what we do on the surface. In fact, of course, the electrodes have a special coating. It's a 7018 electrode. We have to remove the slag just like it's done on the surface. We also have to brush it to ensure the weld is effective. But it's done exactly the same way as it is on the surface. The only difference is that here we reverse the polarity of the cables so that the metal surface is the one that heats up more, making the weld more effective. That's the only difference, that the polarities are reversed, but it's a normal weld. I remember I was trying to remove that griphicle, and the guys above were cleaning the other anodes, and bits of coral and shells were falling on my head, and the fish were pulling my hair because they were having a feast there, eating all around us. But I'll say it again, I was and still am passionate about it. For 22 years, I had to do exactly the same job this way. Well, as I mentioned to you, the anode replacement procedure was typically carried out every 6 years, or sometimes extending to 7 years, which was a significant maintenance interval. So this was okay, everyone, as I was explaining earlier, for the crucial potential measurements, there would consistently be one dedicated person responsible for conducting and overseeing the entire process, ensuring accuracy and safety throughout the operation. Sorry, let me activate the pen. The person is always here with their multimeter. One individual is positioned here, making direct physical contact with a specific test point that is always permanently installed, which is essentially a dedicated test station. They establish their physical connection while the other essential cable extends to the silver chloride cell, which is equipped with a carefully balanced counterweight. This counterweight is crucial so that the skilled diver can precisely place the cell in the exact positions where they have been explicitly instructed to do so, specifically where the electrical potentials absolutely need to be accurately measured. So the critical question then becomes, how exactly did I effectively communicate to the divers the precise and detailed measurement sequence that needed to be followed? Normally, I first had to gather everyone together, have a full meeting, and explain to them how things were, how I had organized the dock. That is, I had each pile numbered. That was the sequence they had to follow during the measurements. I had all of them numbered, and where you see the little red squares, those squares are where I had installed the corrosion coupons. So I would tell him, all right, you're going to go to pile number 1 of mooring dolphin number 1. This stands for dolphin mooring number 1, dolphin mooring number 2, and so on. I would tell them, I want you to do this. When you're in the water, you're going to take a measurement for me. Sorry, no, I hadn't activated the pen. The first measurement you're going to take for me here, near the splash zone, near the splash area. You're going to take a second measurement next to the anode on the back side. You are going to take a third, very important measurement for me right here. You are then going to take a fourth, equally crucial measurement here, and then another final one here, completing the set of necessary readings. Here at the bottom of the seabed, he had to, with a pick, clean the surface. The diver had to clean the surface for me here and place the silver chloride cell right against the pipe. That way we eliminated error after error. And this was the sequence. On pile 1, you're going to take measurement 1, measurement 2, measurement 3, measurement 4, and measurement 5. So each pile should have at least 5 potential measurements. One near the area with a high concentration of oxygen, one near the anode, one at the midpoint, one at the next anodes, and another where less oxygen reaches. Logically, you might be asking, Pedro, why are there 3 distinct anodes in your particular design? Normally, let me just erase this section here. Normally, this specific anode, let me activate the pen tool once again. This substantial 50 kilogram anode was originally intended to provide comprehensive cathodic protection to this entire designated area. And these two 100 kilogram anodes are intended not only for the part that's in contact with water, but also for the part that's buried. If this pile is 25 or 20 meters long on the seabed, it also has about 30 or 40 meters in length driven in. In other words, it's buried in the seabed. So these anodes had to compensate for both the protection here and what is buried. That's precisely why, in this particular case, it was consistently measured in that specific manner. So basically, my dear friends, this is the fundamental sequence for accurately measuring electrical potentials. These two people, both the person on the platform and the diver, have two-way communication. That is, the diver says, I'm at 2 meters, and the person above takes the potential reading and the depth, and takes the depth into account. The diver says, 2 meters, I'm at 5, I'm at 7, I'm at 10, I'm at 15, for example. And he and the person, there has to be another person measuring and recording. One person does that. It's not necessary to have two people. So that's the measurement sequence. And of course, I had my doc, as I mentioned, clearly marked so that they would know exactly how to carry out that sequence of measurements. It's difficult to find an inspector who has experience in cathodic protection, and on top of that, who has experience and is also a diver, someone who has experience in underwater inspection. Normally, for the regulatory authorities, I demonstrated the effectiveness of the cathodic protection through corrosion coupons. This is a technical report, but I want you to look at the photographic records of the coupons with protection and the coupons without protection. Take a look at this. These are coupons that I installed as I showed you in the schematic. I already had identified where I had installed them, and this is how the coupons looked when I removed them, both the protected and the unprotected ones. When I meticulously performed the detailed chemical cleaning and subsequent pickling process, notice how I carefully found the completely unprotected coupon, and in stark contrast, the coupon that had been provided with cathodic protection. You can clearly see that the protected one was practically always intact, appearing almost like new. You could even distinctly read the identification letters that were inscribed upon its surface. In this particular case, it prominently says Dam 2P3, which precisely means Duke Amar 2, Pile 3. This designation helps to accurately identify its specific origin and purpose. And this was my way of showing the regulatory body, look, I'm not just monitoring, not just checking, not just managing the mechanical integrity, but this was the way I could demonstrate to them that I was protecting all the submerged structures against corrosion. Now, I know someone is going to jump in and say, oh yeah, but tell me about the numbers. What were the values, the corrosion rates you were seeing? Calm down, my children. Calm down, my guys. Take a look at this example. This is the corrosion rate table for unprotected coupons, meaning coupons without any protection. The corrosion rate or corrosion velocity was always between 10 and 12 mils per year. That was the corrosion rate of the coupons that didn't have cathodic protection, but for the coupons that did have cathodic protection, which is shown in the table of protected coupons, notice that we reduced the corrosion rate to 0.37, 0.25, 0.32, almost down to zero. It's impossible to bring it down to zero, but at least it was reduced to the minimum permissible level, or rather the maximum permissible, or better said, the lowest possible level. So this was one of the ways I could show the regulatory body. Look, the corrosion rate was normally always between 10 and 12 thousandths of an inch per year, and I'm bringing it down to 0.56, 0.32 thousandths of an inch per year. So this was how I could demonstrate to the regulatory body that we were achieving the objectives. And of course, there was another very important type of report, which was specifically the sizing report. The sizing report, well, that particular one was quite significant and provided crucial details. They were trapezoidal anodes. They had to measure the length, the width, the depth, calculate the mass, and with that we could determine regarding the anodes, look, this anode is going to last you 7 years or 5 years. And then I could create purchase orders in the SAP TM system, and I could plan ahead and buy the materials, request my budget, request my funds for the purchase of materials. Every diver welder, I would subject them to testing just as the standards required. These are the test specimens that I would have made after they performed their underwater welding. I had to send these specimens to the lab for tensile tests, hardness tests, bend tests, liquid penetrant tests, magnetic particle tests, and I even had to have them undergo radiography. And after they gave me all those test results, the diver would be authorized to perform underwater welding in my facilities. These are the installer. These are the vessels we used for diving operations, where we had the compressor, the reserve air tank, the emergency air tanks, and the umbilicals. This the system of diving operations. This emoji of I was young when I was 30 years ago. But anyway, when I would put on my diving suit and start working with them, as I told you, it would always catch them by surprise. What else am I going to tell you? Oh, okay. There is a manufacturer in Venezuela that makes both current and impressed anodes as well as galvanic ones. And just look at the variety they have. This company is called Diprocable. It's located in Maracaibo, Zulia State. I once went to their factory of my great friend Juan Gil. I saw the manufacturing process. They are ISO 9000 certified, and that's why I always used to buy their products, at least these bracelets for the underwater pipelines. These are bracelet type anodes for the well joints, and they had them for all diameters, whatever diameter you asked for or required. They had those varieties. Well, guys, here in this photo, you can see what the aluminum trapezoidal anodes look like. These are incredibly massive 200 kilogram anodes, and normally we meticulously use specialized balloons to be able to carefully install them onto the substantial piles, and then immediately afterwards we precisely weld them to the robust piles of the docks. And this particular example clearly illustrates what these impressive anodes look like physically in their final form. Normally here you should apply a layer of tar. On this side, you should apply a layer of tar. That is, this anode has to be separated about 30 centimeters from the pile. But on this side, you need to apply tar or an insulating resin so that the current from the anode does not flow directly onto the surface of the tube because it would wear out very quickly. So when we only allow the current to flow through the lateral sides, it distributes more evenly all around the tube. That's another tip I wanted to share with you. Well, guys, I hope this video is helpful to you. If you ever face the challenge of doing inspections at marine terminals, don't be afraid. It's the same as what we do on land, just more specialized, at least from the perspective of diving operations. To wrap up the chapter on underwater inspection, PDVSA has work procedures for everything, even for going to the bathroom, believe me. These are companies, corporations that have procedures for everything, and they have their own internal standards for safe diving operations. I was part of this committee. I was a member of the Underwater Inspection Committee, the Coatings Committee, and the Cathodic Protection Committee because I always had something to say. And in diving operations, it's not that I was an expert in diving operations, but I did have something to contribute from the perspective of specialized inspection. Remember I told you that in my technical explanations, I always specified that the contractor had to provide me with 2 sets of equipment, or that 2 sets of equipment had to be available for me. Because I always tried to train the personnel under my supervision, you know. I even encouraged, when no one in my department wanted to do it, I tried to motivate someone from another department, you know, to see if maybe they'd fall in love with cathodic protection. But I was obligated to explain to them the risks and why underwater inspections are considered one of the most dangerous jobs in the world. I'll explain why in a moment. Normally, both you and I, or anyone who works in an office, right now we're breathing regular air. That air is made up of 80% nitrogen and 20% oxygen. That's the essential air we absolutely need to breathe and ultimately survive, right? However, during extensive diving operations, we also breathe the very same air that you and I are currently breathing right now. But when we're under pressure, underwater, we're at different atmospheres. Every 10 feet, we change an atmosphere. Every 3 meters of depth, the atmospheres increase. And that nitrogen in the form of gas that we're breathing, at those pressures, that nitrogen starts to circulate in liquid form through our bloodstream. And well, we have limited time to carry out diving operations. What happens if I ascend to the surface abruptly or uncontrollably without waiting for that nitrogen to turn back into gas and for my body to expel it in gaseous form through my breathing, through my sweating? Diving operations require, or rather, there are decompression tables that restrict these operations. For example, let me give you this example. Let's suppose I'm going to work at a depth of 30 meters or 100 feet. Let's say we're going to work at a depth of 100 feet. That's roughly 30 meters. What does the table tell me? The part that's in white represents the operation of, these are safe diving operations. For example, when I'm at 0 to 16 minutes, if I work 16 minutes at that depth, I only need to ascend before surfacing and wait 4 minutes. Okay, great. But if I work between 50 to 70 minutes underwater at that depth, I have to ascend 10 feet, stay there for 3 minutes. Then I have to ascend to 40 feet, up to 40 feet, and stay there for another 3 minutes. Then I have to ascend to 30 feet. I don't know what's wrong with this pencil, and I have to wait 10 minutes. When I get there, as I'm approaching 20 feet from the surface, I have to stay there for 20 minutes. And just when there are 10 feet left before surfacing, I must stay for 45 minutes. The total time I have to wait before surfacing is 81 minutes. That means if I worked for 70 minutes, I have to add another 81 minutes before I can surface, and I can't keep diving anymore. So there are some waiting times, nitrogen time in the surface reserves, which are other calculations. But what this is telling me is that no, it can't be. This is an internal corporate policy, so it must be strictly followed, and I am required to comply with it. That's why diving operations are dangerous, and I had to explain this to the people I was teaching to dive. I was telling them, if you're at this depth, which was our normal depth, and you spend these minutes underwater, you can't surface until after 81 minutes. You have to ascend gradually, staying for certain periods of time at each level. The dive supervisor keeps track of these times for us and tells us, Pedro, you've reached the time limit, ascend to 30 feet, go up 10 feet, and stay there for 3 minutes, and so on. He would progressively instruct me to change depth so that the pressure exerted by the water on my body would decrease gradually, allowing my body to eliminate the nitrogen that was circulating in liquid form through my bloodstream, expelling it through breathing and sweating. Because if I ascended abruptly, my veins could burst, my kidney could burst, my lungs could burst, my liver could burst, my brain could burst, and I'd be knocking on St. Peter's door. There are other tables, commercial ones or ones that aren't very safe. The SCI and PADI tables simply don't work for us. They're not truly suitable. For example, here's another dive table for the sea. And notice that for 100 feet, I'll use this as an example here. For 100 feet, which is this one here, I have to follow these specific times. That is 3 minutes plus 45 plus 22 plus 2 plus 3. Sorry, plus 2. This gives me a total of 45, 67, 72 minutes. So this is 10 minutes less. The PDS table is much more conservative and forces me to stay longer, and for us divers, that's much safer. I'm following the rules, and it's strictly enforced and absolutely mandatory, and no one can force me to say, get out. No, it's my soul, my life, not yours. It's my life, not yours. So basically, I had to explain this to the guys. This is the risk you're going to face, but I'm obligated to explain it to you and make sure you fully understand it. Of course, many of them got quite scared. Well, guys, I hope this introduction on how to take potential measurements and conduct underwater inspections will be useful to you in the future. Have a very good morning, a very good afternoon, or a very good night. It's a pleasure to share another little drop of my knowledge with you.